Well, thank you for coming so numerous today, and I'm absolutely not intimidated at all. So this is on von Neumann probes and Dyson spheres, what they are, why they're cool, and why we should care about them. The main reason we should care about it is because it's about the Fermi paradox. So let's start with that. The Fermi paradox simply is, universe is big and old, where are all the aliens? Basically, for most reasonable estimates that you can do about how likely life is to evolve, to become technological, to spread out, and how fast it would spread out, if you then plug them into the number of stars that you have in the galaxy, you come up with there must be a lot of civilizations around, and yet we don't see anything. So the Fermi paradox is the tension between that.
Do you want to come sit up here?
Yep. Take these chairs.
Stuart, what do you finish with this chair, I expect, for the next hour or so?
Well, people outside want to come in? Yeah, you want to ask people outside? So. You have to stand here. Sit on the floor. Sorry.
Now that's the Fermi paradox, and why should we care about it? Well, first of all, because it gives some information about what the fate of intelligent life in the universe is, a set that we're arguably a member of. It has lots of applications: biology, cosmology, ethics. And finally, it may determine the future fate of galaxies. If intelligent life can spread over an entire galaxy, then within a few million years it can probably reshape the galaxy to whatever shape would be more efficient. But the Fermi paradox, it sounds a bit simplistic, so surely there must be a simple solution, a simple explanation. Oh yes, there are. These are some of the explanations that people have come up with. There are many more. This is just a small sampling. You can group them if you want in terms of ones that are good news for us, bad news for us, and mixed news for us. But all these explanations suffer from one crucial flaw that is the same in every case, which is that they're not good enough. The ones that have aliens with peculiar motives also need that all the aliens have uniform motives. The Earth itself is really a middle-aged, middling planet, as far as we can tell. There's no evidence of it being special, and life is rather hardy. There is the correct number of zeros in that quote. And signaling is doable, and spreading out seems to be fairly doable. So what do you do when you have a problem and all the explanations are insufficient? Well, you make the problem harder. So I'm going to be using exploratory engineering. So what that means, things that are compatible with physics and plausible in the future. Here you have some performance metrics. Here you have things that we know we can't do. Here is what we're already doing, and exploratory engineering lies here. Now, that's a cool graph, but what does it mean? What does it mean in practice? So let's give us a few thousand years. What are we going to have? Well, obviously, robot butlers and teleporters. Well, if we're not going to just sort of predict the future through comics, we need to actually have some sensible principles. The first one I'm going to be used is, if it's been done in nature, we'll probably be able to do it ourselves. So that means that I'm going to take artificial intelligence and replicating cells as plausible things we could develop over 1,000 years. We could develop them, or we could co-opt the intelligences and replicating cells that we already have in nature. A second principle is that tasks can be automated. We're pretty good at doing this already, and if we have artificial intelligence, we're going to be even better at it. Amongst the tasks that can be automated is the building of needed machinery. So putting these together, it means hence scale is not in itself an insurmountable barrier. At some point, I'm going to talk about disassembling a planet. And disassembling a planet is basically disassembling an asteroid, except doing it again and again and again and again. And if we have the resources to build the factories to do that, then I'm going to take that as doable. The main problem is, of course, you need a lot more energy and material if you want to disassemble a planet. So that's what I'm going to take as the real limiting factors: energy, material, and time. Now let's focus on humanity. I know it's about the Fermi paradox, but to see what aliens could do, let's first see what we could do. Imagine everybody on Earth, we come together, we agree, let's go colonize the universe. Could we do it? Well, a few important questions. How do we get the energy? What would we send? What do we aim at? And how long would this all take? So first of all, the energy. Well, the conventional and reasonable solution is a Dyson sphere, or shell, or swarm, or bubble, or other variants of that. This is basically getting solar captors around our sun to capture a large portion of its energy. It was proposed by Dyson in 1960. There are a few different models. The shell, which you always see in science fiction movies, an actual sphere around the sun, is completely impractical. The tensile strengths inside it are immense, and also, since it's a sphere, it has no actual gravitational binding with the star inside, so it would drift. Swarm is the more realistic model. Lots and lots of solar panels in different orbits. It's a bit harder to organize, but that's not an unsurmountable barrier. An interesting variant is a Dyson bubble, where you have a solar sail as well as a solar panel, and that would be balanced by the gravity and the solar wind pushing on it. We would need ultra materials to do this, but possibly alien races with hotter stars could do it without needing that. Some mixture of bubble and swarm might be also possible. So, in order to do that, if we wanted to do that, we'd need a convenient source of material close to the sun. Now, where could we find that? So, here's Mercury. What do we know about Mercury? Well, this is its mass, rather large. Not large for a planet, but compared with most other things. I'd say we'll take half of the mass of Mercury to be usable, mainly the iron and the oxygen. That can make hematite, which is a reasonable construction material. This is the usable mass. If we made a sphere in Mercury orbit made of this usable mass, it would be 245 grams per meter square. Since the surfaces are mainly going to be floating in space unsupported and reflecting down to concentrate the power in whatever generators that we put, this is not an unreasonable estimate. If we were willing to move them closer to the sun, we could put more material per meter square. How would this proceed? Well, get energy, mine stuff, get it into orbit, make solar collectors, which give us energy. And as long as we can automate the whole procedure, which is one of the assumptions that I made, this, by the way, we could do it now. We could get to Mercury, put some solar panels, get some mining stuff, and get the whole procedure done. The question is, if we can automate it and have the factories built, then could we do it?
Does Newt Gingrich know about this?
Yeah, he said it was. He said it wasn't exciting enough for him to mention.
Can I ask a question? I mean,
Yes?
if you want to make the solar collectors, do you have enough of the rare elements that you need to make efficient solar collectors?
I said solar collectors, and I showed a picture of solar panels. It's, as I say, it's mainly going to be mirrors is the more efficient way of doing it. Lots of mirrors concentrate out. Then, where it's concentrated, you need some sort of rarer things with solar panels or heater pumps or something like that. But the mass of the thing that generates energy is a lot lower than the mass of the whole structure. So that's why I didn't focus on the rare elements that we'd need.
But even then, there are going to be limitations because I mean, you can't put an infinite amount of energy in a finite amount of space and expect any technology to turn it into useful power. Right? But that's just not a problem.
Well, there's a bunch of other minerals in Mercury, not just oxygen and iron. But maybe I should look at that. This was a first pass.
It's worth noting you can do a steampunk version, of course, just with boilers using all that oxygen, for example, and a lot of steam. It would be ridiculously inefficient, but you could just use iron and oxygen in this calculation just for that.
It's mainly the heat that we're trying to capture, not the high entropy of the photons.
Well, the low entropy, in fact.
Sorry, rephrase that. Not the low entropy, the high negentropy of the photons. Now, what are the assumptions that I'm doing? 10 years to process and position the extracted material. That's, I'd say, a very conservative assumption. About half of it usable. 1/10 efficiency for moving the material off planet. The rest goes into breaking chemical bonds and mining. 1/3 efficiency for solar panels, and initially a tiny 1 kilometer square of solar panels on Mercury to power it initially. Under those assumptions, what happens? Well, this is a log graph of the power that we generate. First 10 years, we're busy processing stuff and building it and placing it, so power doesn't go up. Then we suddenly surge. Then 10 years after that, we surge again. We go to a faster regiment where now we're building things faster and faster. Then another surge, and then the beginning of another, but why did I stop the graph there? Because this is the mass of Mercury. So in about 4 cycles, we've completely disassembled the planet. And the real reason that this happens is because it's all exponential. There's the feedback. We get it into orbit. We get more energy. That powers more stuff. And as long as it's exponential, in a certain sense, the initial assumptions don't really matter. It'll happen fast. We could disassemble Venus in just, I think, a year more under these assumptions. So the real question is, can we get the exponential feedback? If we can, taking Mercury apart it's easy. Now,
I looked at this, so there's only 4 generations. You're saying that you only build in 10 years periods.
Yes. No, it takes 10 years for the material. The material mined here will start giving us useful power here. So it takes 10 years to place the object in orbit, make it into a solar panel, and have it start being useful. I'd say that I chose 10 years because I think around here, a 10-year estimate when most of the sun is already covered is probably realistic. Initially, it'll probably to do it in months or weeks because you don't have to move very far. But 10-year overall seems a reasonable, conservative estimate. Now, with all that energy...
Are we using most of that energy to continue the process of disassembling the planet?
Yes.
So we're just... And the useful part of that energy is just a tiny proportion of what we're... Is the energy you're generating, is it mostly needed to continue the process of disassembling Mercury?
Yes.
So how much of it are you actually extracting for other purposes?
Well, none in that estimate.
So this is just a sort of like a gratuitous Mercury disassembly disassembly exercise.
Yes.
I thought we were going to...
No, but 40 years after 40 years, we've got a machine, right?
Yeah, after 40 years, we're done, and now we have quite a lot of energy. And as I say...
Like fusion.
What,
It's not about you, Alex.
as I said, I was assuming one...
Do this cheaply.
I was assuming... I doubt you could get 4 times 10 to the 26 watts, particularly cheaper.
But you need most of those watts to produce, to disassemble the poor mercury.
But as I say, it's exponential. If we say that we use half the energy to, I don't know, power our televisions, it still will go to something like 45 years instead or something like that. It is the exponential thing that's really saving us. Now, we've got the energy, and with that we can power mass drivers. Why am I saying mass drivers, not rockets? Because the relativistic rockets equation is evil, as we shall see. So power mass drivers to shoot our probes away. Yes, that probe is pointing in the right direction. It's been shot, and it will need to decelerate upon arrival.
So mass drive is just firing something at your rocket to push it away?
Well, it's actually the rocket starts here and gets shot out. There's various designs for how that can be done.
What's mass drive?
Oh, basically electromagnetic shooting machine. Not quite a railgun. There is a critical difference between the two that I don't understand.
The railgun, you need contact with the rails, and then you of course need to deal with a rather nasty problem of friction and plasma discharges and stuff like that. But you can imagine just like a big particle accelerator sending a magnetic particle at very high velocity. In this case, the particle happens to be a spaceship.
Yeah.
What the guy said.
Yeah, I mean, it's the linear motor technology that years ago of Braithwaite and other people.
Now the question is, what would we send? What would that little rocket with the scared man be? So von Neumann probes, which is just another way of saying self-replicating probes that can make more copies of themselves. What's the simplest design for a von Neumann probe? Well, I'm going to give you one we could probably build today. Start with a couple. Actually get a bunch of couples. Get some life support. Data, of course. A factory. An engine. And here we have a von Neumann probe. It's not the best design for a von Neumann probe. The actual payload is hundreds of tons at least. It's got a limited acceleration because of the people on it. But you can imagine ways of improving this. There's ways of freezing people like in all the sci-fi movies or whatever. The point is, this is a von Neumann probe. It would work. It would copy itself, and we can arguably build it today.
Only if the people's motivations are reliably copied.
Yeah, there is that. And getting people to volunteer might be a bit tricky.
Well, they're going to be brainwashed from birth, right? So
Though actually by entering this room, you've all agreed to volunteer. But let's look at some more mechanical designs. This is the Bracewell-Freitas self-replicating probe, designed in the 1980s, based on the Daedalus design and the NASA self-replicating lunar factory. The payload is 500 tons. It requires basic AI, and it has a 500-year replication time. It's not the most efficient design ever, but the point of it is that it can be done. With the basic AI, it's very conservative assumptions, and it can be done. So
can I just ask, the idea of this is that it goes to another solar system, takes resources from that solar system,
yes,
builds copies of itself,
and they go.
Propagate.
Yes. And again, even though it's 500 years replication time, it is as another exponential growth, so it can take over a galaxy reasonably fast.
So what sounds quite evil?
Yes, we'll get to that later.
but what's it actually accomplishing? I mean, it's just a machine, right? You're
Yeah.
self-replicating that machine.
Yeah.
But you can make other things.
Oh, yeah.
So what's the use of it for us? It's not. We're not even there to watch.
Again, I'll get to motivations towards the end because they're rather interesting.
It's the first one, but nice.
This is a large self-replicating probe. Let's go to the other end and see how small it could be made. This is the Merkel-Freitas molecular assembler. It's theoretically possible of self-replication. It's rather light. Even if you had an interface with the environment so that it could extract resources and move about in simple ways, it's still extraordinarily light. So this is kind of the lower bound. We've seen the upper bound. Let's try and get a reasonable estimate. First thing to mention is that the data storage is not going to be a problem. This is the most efficient data storage we could realistically get. Get a diamond, carbon-12, carbon-13. Carbon-12 is 0, carbon-13 is 1. This thing can store a huge amount of bits. By comparison, this is all the world's data. If you view people as brains as being defined by neurons and connectivity between neurons, you could say that a human brain is about 100 terabytes. So this 1 gram of diamond can contain all the world's data and the population of Britain. I'm not seriously arguing that we're going to send diamonds with the whole population of Britain and all the world's data to the stars, fun though that would be. Or that the data storage is going to happen in this way. I just wanted to point out that the theoretical limit on data storage is very large. There is a Moore's law for hard drives, so it's probably going to continue for quite some time. So most likely the data for the simple AIs that we need are not going to be critical. Maybe a gram or 2. Now, what about the replicator itself? As I said, we're going to look to nature for some inspiration. This is the smallest general environmental replicator. E. coli is quite robust and is barely bigger. Smallest seed, a millionth of a gram. The seeds are very interesting because they're small objects that create large objects. The smallest acorn is 1 gram, and the acorn is lovely because it is a solar-powered system that grows into a factory that produces more acorns. That's exactly what we want. Now, we'd be giving our probe some nuclear power, because you can store energy quite compactly there. So it needs legs, drill, roots to extract resources. Biology has all of these, and these can be made quite tiny. So I'm going to put this all together and estimate a 30-gram probe, including the data. Now, I think this is a reasonable estimate for what could be achievable, but do keep the 500-ton number in mind as well as an upper limit. So, we've got a von Neumann probe, we've got the payload, it's been shot at high speed to another galaxy, and it's not all that good if it just slams into the other galaxy at high speed. So we need to decelerate it. There are fun ways we could do it with sort of the ramjet, but let's ignore that. Let's just look at rockets for the moment. The relativistic rocket equation. MO is the final mass, which is 30 grams. M1 is the initial mass. And ISP over C is basically the efficiency of our engine. I'm going to use 3 different models. I'm going to use a fission drive, which we know we can build, a fusion drive, which we may realistically be able to build, and a matter-antimatter drive, which we may or may not ever be able to build.
If you're decelerating with the rocket, why didn't you accelerate with the rocket at the beginning rather than destroying Mercury?
Because, well, we destroy Mercury to get the energy.
Yeah.
And we don't accelerate with a rocket because this equation is a bitch if you apply it twice. It would be much, much better to build a huge mass driver to launch it to the speeds required. Or else you need really brutal amounts of stuff for most of these. Then I looked at 3 different speeds, 50, 90, and 99% C. And these are the reaction masses that you need for all of them. I'm going to look at these three as being interesting. So matter, antimatter at 2.5 kilos, 7 tons, and 28 tons. Rounding these up, so I'm going to look at probes of mass 3 kilos, 8 tons, and 30 tons. Now, we've got our probes, we can launch them, they can decelerate. Where do we send them? Now, everybody seems to be assuming this kind of model of universal colonization. But this is another model.
Sorry, quick question. You jumped from stars to galaxies.
Yeah.
Presumably deliberately. Could you just say something about the motivation?
I never talked about stars.
Okay.
Did
well,
I?
I just assumed that so the limits you're going to end up deriving are most
Yes.
useful when you consider galaxies.
So to clarify, this is colonizing the universe, galaxy by galaxy, not star by star.
But we haven't yet sorted out the stars, have we? We've already colonized all the stars. Right?
Yeah.
No, we don't need to. No, well, as we'll see for the numbers, it actually, under these assumptions, we can start the colonization of the entire universe in way less time than it would take to colonize the Milky Way.
I thought the estimates for colonizing the Milky Way were a few 100,000 years by these one Neumann probes. You could basically colonize every single solar system in the Milky Way.
Yeah.
Well, it takes a few 100,000 years.
This is not the time taken to colonize the universe.
Start colonizing.
To start it, to launch all the probes that will then do their jobs. But, okay, so the question is why this model isn't, why blast all the galaxies at once? Well, the main problem is that our universe is expanding, and we seem to be on an exponential increase. So if we don't get to some places fast, we'll never get to them. These are the geodesic equations in co-moving coordinates using current light years. At 50%, 90%, 99% c and the speed of light. This is about how far we can get in the universe. It corresponds to this number of galaxies reached at these three speeds. Approximately. My estimates on the number of stars per galaxy are very crude, but I haven't found good ones. And delaying the launch has virtually no impact on these figures. We can wait 1 million years, they'll still be about the same. So basically the best would be wait, take all the time we need, and then blast it really, really fast. So, how long would this all take? Well, there's a redundancy. How many probes do we need to send to each galaxy? There's cosmic dust. You can model that in various ways. Collisions. There's fun ways you can protect your probe from it. Electromagnetic things. Lots of cunning stuff. It's all very vague. So I'm decided on a redundancy of precisely R to be determined. Now, this is our three models. The speed, the mass, the kinetic energy needed, and for the matter-antimatter, we're also going to need to generate the antimatter, and the number of probes, which are dependent on how many galaxies we can reach. The total energy is in the 10 to the 28, 29 kind of area. So, this is the energy we need to send out all our probes. We have our sun. We're getting all its energy at 1/3 efficiency. How long would it take? Well, to blast the entire universe, about 7 minutes, 4 hours, or 1 minute. The reason this one is so high is because, well, fission is low because even though it's a high mass, it can't go very fast and we don't have many to send. Fusion is in the middle, and matter-antimatter helps for being such a low mass.
I'm kind of worried about this because you ignored entropy, right? And you're just assuming that we can use all of the energy that we get from the sun to put into these probes.
I'm assuming that you can use 1/3 of the energy.
Yeah, but you might be off by orders of magnitude.
Yes.
Depending on
I feel
what
I can
you have to...
I feel I can afford some orders of magnitude. And remember the 500-ton probe, so the upper limit. This is how long these would take. And I think I can say that, well, if R is reasonable, then on a cosmic scale, the approximation of these numbers is 0. In the blink of a cosmic eye, a civilization could decide to blast the universe with self-replicating probes. Of course, they're not going to spend all their energy building probes. They have soap operas to watch as well. So, but if you imagine, say, of 2,000 years, a civilization has 4 or 5 stars. They're generating all this energy, and then occasionally they blast off this from the surplus they get. Again, in cosmic times, it's not going to take long. Now, and to answer the previous question, once we blasted the universe, then the galaxy will take about the same time. Blast a probe to each star in the galaxy and take over it. So actually, if we wanted to say to colonize every star in the universe, it's 2 waves. You blast every galaxy, and then inside the galaxy you blast every star.
Well, ignoring travel time, right?
Of course, it takes forever.
I'm talking about the amount of time to launch these things.
Yeah.
Yes, it's to actually be sure to, by the time you have claimed what you want to claim, it'll take a huge amount of time, and some of it will have moved outside of your...
Yeah, so your 1 minute doesn't really mean doing much. You're not doing much in 1 minute.
It's
You're just
launching. It's pressing launch button.
You start,
So, enough about us. That's all fun and entertaining, but the real reason is to look at the Fermi paradox. So, we could do this. What if other civilizations decide to do the same? This is looking back into the past. These are billion-year marks. And this is 50% C, 90% C, 99 C, and C. So if a civilization could go at 99% C and back in 5 billion years, we're talking about several billion galaxies that could reach us. Even if you're more conservative, say you're going half of C in 2 billion years, that's still at least 4 million galaxies in reach. And 4 million galaxies is about 1 million trillion stars, which is quite a lot. Now, let's get back to the motivation thing. Why would you do this? What possible purpose could you have to blast the entire universe? Well, first of all, there's certain subgroups who would want to expand. Total utilitarians, for instance. Some religions will find this kind of expansion very compatible with their theology. And yeah, the British Interplanetary Society and other groups, they really want to do this. They've got plans for it. If they were given the energy and the resources, they'd be off. And some may want to escape. Maybe you want to escape your government or your dominant faction or whatever else. And the interesting thing for escape is that if you just need to send a few probes, so not colonize a lot, but just send a few probes, you can then concentrate on them and send them at speeds so fast they can never get caught using the expansion of the universe.
I'm talking about why people want to go to other stars and galaxies.
Yes.
It's all the calculations you've done about sending tiny probes.
No, the 500-ton one was people, possibly.
Right.
Yes. And there's also assumptions whether you can put yourself into AIs or that kind of format, or put human brains in a format that is resistant to these kind of accelerations.
So you store the morons in the diamond that...
Yes, Anders suggested sending the population of Britain inside the Koh-i-Noor to the stars, which would be a very appropriate use of the crown jewels.
But you don't need to ask this question.
But
you've got 1 trillion different aliens to do this.
Yeah.
You don't know what their motivations are. You don't need to.
Well,
one of them just needs to.
Yes, but the motivation is if there are humans are our main model for what aliens might be like. And if humans would want to do it, then the chances that a random alien species might also want to do it are higher. As I said, there's another way is to prevent these. The best way of preventing, especially the escape, is to get there first. You might want to ensure your civilization from collapse. If you're spread out, then a disaster is not going to wipe out the whole civilization. And lastly, there's a game-theoretic consideration. Lots of civilizations, I feel, would be perfectly fine with not grabbing the universe. But they would not be fine with other civilizations grabbing it and getting all these resources and surrounding them. So in order to stop them from getting it, we need to go there and grab it first. Because they're untrustworthy. Because they're going to try and grab us first because they don't trust us. And so to prevent them from grabbing it first, to prevent us from grabbing it first, we need to grab it first.
So aren't you arguing that Hemspermia or whatever is correct and we're the aliens? We're already the alien species, right?
I don't quite understand that.
We're the result
of somebody having grabbed the universe.
Yes.
I feel that would be very unlikely.
No. The very first civilization has made exactly the set of arguments, right, and said we better go first. They've sent it out. They've colonised the universe, and we're the result.
Remember the slab in the Kubrick movie?
Yeah, but
that's true.
But I feel it would be very unlikely that you would colonize using, say, beings that would then forget where they came from, or
no. You colonize in a different way. You send in. You do the slab in 2001. Indeed.
No, this is the moment when we are realizing that this it was all planned.
No, but seriously, I mean, you've argued that it's very efficient, right?
Yeah.
Hmm?
And you've come up with exactly the motivation that Joe was pointing out.
Somebody
So
must have
why aren't you making a case that we are? Why aren't you making a case that we're aliens?
Yeah, we are aliens.
well, because
we are failing in that case in protecting ours and the area of grab. If our ancestors sent us out to grab the universe, we're doing an awfully bad job. If some other aliens showed up in the solar system, we couldn't actually currently prevent.
There are no other.
No.
Well, but we can't prevent any other aliens from coming there. The problem is
No,
we're inefficient as guards of the solar system actually right now, and we were even less efficient in the past.
But this argues...
No, but that's a very small time scale. The period over which we're inefficient is incredibly short.
Yes.
and the other point is we don't remember our alien progenitors.
No.
Well, then that means we're not guarding the solar system for them. But remember, the point is, if you want to grab this to prevent other people from grabbing it, you don't want whatever you've grabbed it with to become independent groups with their own motivation.
But there are other motivations, I think, at one point. There are other motivations than just doing a land.
But, okay, if you want, I just feel it's very unlikely that there is some model where a technological civilization successfully grabs a planet or a solar system and then forgets everything that it had.
What if they just want to spread their genetic material? I mean, when Genghis Khan conquered most of Asia, it's with a lot of women apparently, they find spreading genetic material.
Again, you can do this better if you keep hold of your technology.
But maybe it's more difficult to hold on to your technology while doing this. Maybe the easiest thing to do is send some basic DNA out instead of sending a whole history of our technology or something like that. Sending the simplest thing out as many times as possible instead of sending...
Remember what I was saying about the data. Putting quite a lot of information doesn't seem to be very hard.
You have to reconcile panspermia with evolution.
Do I?
Well, people are saying that we're aliens. You have to reconcile evolution with history. Well, maybe the original life.
We're getting into bad stuff.
Anyway, I'm nearly at the end.
The world did start 6,000 years ago.
So,
everything else was on the diamond as information.
So, I've basically shown, I believe, that it's not too hard to do this sort of mass expansion, starting it in a very short time. And I've shown that there's lots of galaxies close to us that are within 2 billion years. I think saying life might have reached technology on other galaxies within 2 billion years of our time is not an unreasonable assumption. So there's lots of galaxies within reach, and again, come back to the Fermi paradox, we don't see them. Where are they? Well, first explanation, of course, it might be that basic AI is impossible, and crude von Neumann probes are impossible. I don't find this particularly credible, especially because it would mean any alien that ever evolved anywhere to a technological level would find it impossible to crew a von Neumann probe. There's, of course, the general catch-all. My calculations may be wrong. There's other theories. They're here, but we can't see them. And there's my most likely explanation. The Fermi paradox is strengthened. Technological life probably much harder than we thought. Here's a selected bibliography, and thank you for listening.
Questions?
If we assume all your calculations are right, using that last point, we can put a limit on what fraction of stars have an intelligent life around them. Because we can say if it happened within the nearest 2 billion galaxies, we'd already have met.
Yes, that's
what that
kind of what I.
That implies that,
that's what I take from my talk.
So that implies that you could. That's a fraction of that solves the Drake equation for you, or that's the answer to the Drake equation, or a lower limit for the.
In a certain sense, yes. For advanced technological civilizations, and I feel that my especially my game-theoretic argument is quite strong, and that if you are technological and you can do this, within a few thousand years, at some point, you will.
Well, unless every civilization that gets this far gets technologically sophisticated to do this, decides ethically this is, this is, as somebody mentioned, this is quite an evil procedure. All right? So maybe they decide there's very strong ethical.
Well, first of all,
that's where the 10 to the minus 7 or 10 to the minus 8 is.
Well, I've just shown that there are groups in humanity who would want to do it.
But not necessarily by the time humans are capable of doing it. We've no idea what human society is going to be like.
Yeah, the point is, it's not that far in the future for this technology.
Well, we have no idea what human society is going to be like in even 1,000 years, right? Because
you can expect that there'll be subgroups with various weird ideas.
No, but all this assumes that the human society is still around in a few thousand years.
Yeah.
Yes.
And actually, there's also an argument of this kind. Gott, I think, was the one who published this in the 90s. That, humans, societies, like, if you estimate how long it's going to be, well, it's thousands, maybe tens of thousands, maybe hundreds of thousands of years. So actually, we don't have a million years to prepare for this launch.
I can actually answer both of the questions in one. It's, yes, there is that. Yes, there's that. But are you sure that 99.9% of every civilization at our level either becomes ethical or dies out? Are you sure that 99.99% of them either become ethical or dies out? Because that's the kind of numbers that we need if this is to be a major explanation for the Fermi paradox.
I don't see why it couldn't be 10 to the minus 7. Frankly, I don't see why it couldn't be only 10 to the minus 7 or 10 to the minus 8 of civilizations reach a certain level and don't have these ethics, right, to forbid this. I mean, it seems to me that they could be a very
civilization. You just need no subset of it. You don't need the whole civilization. You don't just require the whole civilization.
No. But the rest of the civilization would provide constraints on those.
And remember, it's not only
vaporizing the nasty ones.
It's not only that you have to be ethical. You have to also be sure that every other civilization you ever encounter is going to be ethical, and so not do the whole grab the universe before they grab it.
It depends on how ethical you are. If you're super ethical, just knowing turn the other cheek.
Assuming that is the correct ethics.
Well, if you are ethical, and there might be some unethical group that's going to take it, I would say that it is your ethical duty to grab the universe first. I mean, you don't have to kill other races. You could just grab it and stop other people from killing other races.
No, but maybe if these groups start replicating in our backyard, right? I mean, there's going to be competition.
Yeah. Well, yeah, but that's a design of the probe kind of thing. But by the time we get that, we'll have some sort of AI, and we'll either wipe ourselves out or we'll know how to control them.
So maybe the first civilization that achieved this level managed to do this procedure, and in every solar system's old cloud, or whatever, put a protection. There's a sort of it's whatever the game hypothesis.
That's the arrived but hidden. It's not a okay. Yeah, I'll take because you've been waiting.
I wanted to say it's so easy to do, and it's been done, which would be my assumption.
Okay.
Right? If it's that easy to do, and you have that long to get here or everywhere, and they need stars to power the next step each time. Shouldn't there be an awful lot of stars we can't see?
Yes. I mean, this is very visible.
We don't think it's something testable. I mean,
it's visible.
If you're looking for lots and lots of matter, you can't detect.
So basically alien civilizations as the dark matter explanation. But I personally feel this is the more realistic thing. It's just...
It's also worth noticing that if you just send out your probes and maybe preclude other civilizations from doing anything, it actually doesn't take much resource. One star in some very remote galaxy goes dim over a span of maybe 1 or 2 centuries. Then there is a little bit weird blue shifted radiation here and there. And then there is one star in every other galaxy going dim over a century. A little bit more blue shifted radiation here and there. And that's all you see. If they wanted, of course, to put up adverts across the universe, they could then do it. But if you just wanted as a nature preserve or something else, it would be very invisible and actually don't take much resources.
The actual thing that I found while doing this calculations is that if you want to send a message, say, to the cosmos, it's easier to send it physically than it is to sort of send it by radio waves. Because kind of radio wave, if you wanted to have radio waves that were visible at the kind of distance we're talking about, you kind of have to turn the Milky Way on and off, which isn't very easy. But sending a probe straight there...
For a single probe is tiny.
Yeah.
You're just sending a single message. Then the cross-section for this thing to be intercepted is tiny. So presuming that argument doesn't...
Well,
it
lands on a galaxy and then can then
so you're going to have
spread.
self-replicating probes as just to send a message.
For instance, yes.
Yeah. You have made.
Yes.
How much is your probe decelerated by CMB backscatter?
Translation?
Well, if you put a charged particle on travel to another galaxy, you will get into trouble because you have inverse Thomson scattering that decelerates your particle.
Well,
because the CMB is coming from one direction, you see the ether wind, and it decelerates you on time scales.
That's the sort of one of the exotic deceleration methods that I talked about. There are ways, maybe, that you could make this even worse, get rid of most of the reaction mass and decelerate by using the galaxy you're arriving at. If you can do that, then it gets a lot easier.
Any more questions? Thanks, Stuart, again.
Okay.